In question 1, we are told that at time t is 0, a small ball is projected vertically upwards with a speed of u meters per second from a point A that is 16.8 meters above horizontal ground. Now the speed of the ball at the instant immediately before hitting the ground for the first time is 19 meters per second, and the ball hits the ground for the first time at capital T seconds. Now the motion of the ball from the instant it is projected until the instant just before it hits the ground for the first time is modeled as that of a particle moving freely under gravity, so we are neglecting air resistance here, and the acceleration due to gravity is modeled as having magnitude of 10 meters per square second, so we're not using the usual 9.8, we're going to be using 10 meters per square second. And using the model, we need to show that capital U is equal to 5. As always, we will start by drawing a diagram to see what's happening. We've got the point A above ground. Now the ball is thrown upwards from point A, and then it comes down, and I'm gonna open up the motion like this to add all the information. So we've got the initial velocity being u, we've got the acceleration being negative 10 because gravity is fighting motion. We are told that the point A is 16.8 meters above ground, and we know that we hit the ground here with a speed of 19 meters per second, so the velocity is negative 19 because the direction has changed, and this happens after capital T seconds. Now I'll be using Suvato equations to proceed to show that capital U is equal to 5. So we've got V squared is U squared plus 2AS. So we've got minus 19 raised to the power of 2 being equal to capital U squared plus 2 times the acceleration of negative 10 times the displacement, which is minus 16.8 because the point at which we hit the ground is 16.8 meters below the launching point here, so the displacement is negative. This leads to 361 being equal to u squared plus 336. This leads to 25 being equal to u squared, and if we take the square root, we get that 5 is equal to u as required. Now in part B, we have to find the value of capital T, and this time I'll be using V is U plus AT. We know that the final velocity is negative 19. We've just established that the initial velocity was 5 plus the negative 10 times the capital T. So we've got negative 19 being 5 minus 10 capital T, which means that 10t is 24. And if I divide both sides by 10, we get that t is 2.4. Now in part C, we need to find the time from the instant the ball is projected until the instant when the ball is 1.2 meters below A. So if we look at the diagram again, we are 1.2 meters below A, so somewhere here. So at this point, the displacement is negative 1.2. I'll be using S is ut plus a half AT squared. So we've got minus 1.2 being equal to 5 times t plus a half times the negative 10t squared. This leads to negative 1.2 being 5t minus 5t squared. I will collect everything on the left hand side to get 5t squared minus 5t minus 1.2 is equal to 0. And I will proceed with the quadratic formula. So we're looking at t being minus the negative 5 plus minus the negative 5 squared minus 4 times 5 times the minus 1.2, and all under a square root, and everything divided by 2 times 5. Now the first solution we get is that t is equal to 1.2, or alternatively we get that t is equal to negative 0.2, which is obviously rejected because time can never be negative. So we say here reject, it's not valid, and we conclude that t is 1.2. In part D, we're asked to sketch a velocity time graph for the motion of the ball between 0 and capital T, stating the coordinates of the start point and the end point of the graph. So we've got velocity against time. We know that we are experiencing a constant acceleration of -5 throughout the journey, and the acceleration is the gradient of the velocity time graph. So we are expecting a straight line with a negative gradient, so something like this. We know that the initial velocity was 5 meters per second, so the start point is 0.5, and the whole journey lasted for 2.4 seconds, and at the end of the journey the velocity was -19, so the end point should be 2.4, -19. Now, in a refinement of the model of the motion of the ball, the effect of air resistance on the ball is included, and this refined model is now used to find the value of capital U. Now we need to state with the reason how this new value of U would compare with the value we found in part A using the initial unrefined model. So if we take into account the air resistance, then this surely means that we need a greater initial velocity so that we still attain that final velocity of -19. So the new value of U would be greater than the one we found in part A, since we need a greater initial velocity to overcome the air resistance but still end up with a final velocity of -19 meters per second. In part F, we are asked to suggest one further refinement that could be made to the model apart from including air resistance that will make the model more realistic. So the first obvious thing to mention is that we could use a more accurate value for G, or alternatively we could say that we could take into account the dimensions of the ball, because modeling the ball as a particle simply means that we completely ignore its dimensions. In question 2, we've got one end of a string attached to a small ball P of mass 4m. The other end of the string is attached to another small ball Q of mass 3m, and the string passes over a fixed pulley. Now ball P is held at rest with the string taut and the hanging parts of the string vertical as shown in the diagram here. Now we release ball P, and the string is modeled as being light and inextensible, and the balls are modeled as particles, and the pulley is modeled as being smooth, and we completely ignore air resistance. Now using the model, we need to find, in terms of M and G, the magnitude of the force exerted on the pulley by the string while P is falling and before Q hits the pulley. So as always, the first thing to do is add all the forces acting here. I will start with the weights of P and Q, so 4mg and 3mg pointing downwards. Obviously, we've got the tension pointing upwards for both particles, and since P is the heavier of the two particles, once it's released, it will start accelerating downwards. So we've got acceleration for P pointing downwards and acceleration for Q pointing upwards. I will then proceed by writing down equations of motion for P and Q. So starting with P, since P is accelerating downwards, we've got forces acting downwards, which is the weight of 4mg, minus forces acting upwards, which is the tension T, is equal to mass of 4m times acceleration. While considering Q, we've got Q accelerating upwards, so we've got forces acting upwards, which is capital T, minus forces acting downwards, which is the weight of 3mg, being equal to the mass of 3m times the acceleration of A. I can add the two up to eliminate T, so we're looking at mg being equal to 7ma. I will cancel out the m, and we arrive at the acceleration being g over 7, and I can then proceed into finding the tension. So the tension minus 3mg is equal to 3m times the acceleration, which we just found to be g over 7. So we're looking at t minus 3mg being equal to 3mg over 7, and therefore t is equal to 24 mg over 7. Now that we've got the tension, let's go back to the diagram here. We are asked to find the magnitude of the force exerted on the pulley by the string. Now the pulley is over here. It's feeling a tension to the left pointing downwards and a tension to the right also pointing downwards. So we've got a total of 2 times the tension acting downwards, and this is the overall force acting on the pulley by the string, and therefore we conclude that this is simply 2 times t, so 2t, which is 2 times 24 mg over 7, which gives a final answer of 48 mg over 7 newtons for the force exerted on the pulley by the string. Now in part B, we need to state one limitation of the model apart from ignoring air resistance that will affect the accuracy of our answer to part A. So the first thing we could challenge is that the string might not be inextensible, or we could also say that the weight of the string was completely ignored in our calculation, or finally we could mention that the pulley may not be smooth. In question 3, we've got the particle P moving along a straight line such that at time t seconds after leaving the point O on the line, the velocity v is given by this expression in terms of t, and we need to find the value of t at the instant when P stops accelerating. Now the first thing to do is expand the given expression for v, so we're looking at v being 7t plus 14 minus 2t squared minus 4t, which simplifies to negative 2t squared plus 3t plus 14. Well, we know that the acceleration is the derivative of velocity with respect to time, so a is dv dt. Now in differentiation we get the power down, we deduct 1 from the power, so we're looking at negative 4t plus 3. And if P stops accelerating, this simply means that the acceleration is 0, and therefore we are looking at negative 4t plus 3 is equal to 0, which means that 3 is equal to 4t, and therefore 3 over 4 is the value of t at the instant when P stops accelerating. Now in part B, we need to find the distance of P from O at the instant when P changes its direction of motion, and it makes sense to start by sketching the graph of V against T. We've got the factorized form of V in terms of T. We know that this is a quadratic with the coefficient of T squared being negative, so it's a sad phase quadratic. I will start by setting V to be 0, so if V is 0, we are looking at 7 minus 2t being equal to 0, or alternatively we've got that t plus 2 is equal to 0, and therefore we've got 7 being equal to 2t, which means 7 over 2 is the first value of t at which v is 0, or alternatively we'll get that t is negative 2. So we can now proceed into sketching V against t. It's a sad phase parabola cutting the t-axis at negative 2 and 7 over 2. We are only interested in positive values of t, and we know that between 0 and 7 over 2 the velocity was positive, while after 7 over 2 it's negative. So this means that the particle changed direction at exactly t is 7 over 2, because for the first 3.5 seconds it was moving in the positive direction, and then it was moving in the negative direction. So exactly at t being 7 over 2 we have a change in direction. Now the question is asking for the total distance covered until P changes its direction of motion. So we're essentially looking for the shaded area here. I'll be using integration to find this area. So the distance here will be given by the integral from 0 up to 7 over 2 of the expression of V in terms of t, which was negative 2t squared plus 3t plus 14 dt. We know that in integration we increase the power by 1 and we divide by the new power. So we've got minus 2t cubed over 3 plus 3t squared over 2 plus 14t, and the limits are 0 and 7 over 2. I will start by substituting the upper limit. So we've got negative 2 times 7 over 2 raised to the power of 3 over 3 plus 3 times 7 over 2 to the power of 2 over 2 plus 14 times 7 over 2, and we can see that the contribution from the lower limit of 0 is simply 0, so there is no contribution from the lower limit. Now if we plug this expression on the calculator, we get an answer of 931 over 24 meters, which is the distance covered from t is 0 up to t is 7 over 2, which is the time point at which p changes its direction of motion.